Hello everyone. So in this session we will discuss about the continuation of the memory system and hierarchy which we were discussing till now. Today's session we will just discuss about the cache memory. Cache memory we all know in the memory hierarchy it is going to be the memory which is available very close to the CPU. It is the one which is closest to the CPU, and it is usually a small sized chip, based memory, and it is well known for its speed. Okay, it is high, it is faster in rate, but of course the capacity of this cache memory will be very much limited, and it is very much noted for its performance. Okay, and the cache memory is generally used to enhance the performance of the CPU because of its faster operating speed, and the size of the cache memory is always limited, and hence the frequently used item only is going to be brought into the cache memory. It stores all the data and instructions, of course, but frequently referred items will be always kept in the cache memory, and because of that, the efficiency of the CPU is going to be increased as the access time required for referring to the data is going to be minimized. And of course it is faster compared to the other CPU memories, and it is also very close to the CPU. So this memory will be available like a chip as shown here. It can be present in the CPU chip itself, then it is going to be referred as on chip cache, or it can be available as separate chips, then it is called as off chip cache. And there are different levels that can be offered at the cache memory. We will usually refer to as L1 cache, L2 cache, L3 cache. So the cache memory can be referred or identified in three levels. So the L1 cache is, of course, the speed is very good. It's going to be very high, and it is going to be very much internal and very closer to the CPU, and the size of the cell 1 cache may range from 8 KB to 128 KB. The next level of cache is usually called as L2 cache, and it is referred as external or secondary cache, whereas the first one is going to be called as the onboard cache or the internal cache or the primary cache. And of course this L2 cache is available to store the data in a temporary fashion, okay, and but which needs a faster access time. And here the size of the L2 cache may range from 128 KB to 1 MB. So as we move away from the CPU, if it is increased in the levels, then obviously the capacity of the cache is going to increase. The next last level cache, L3 cache, is called as it is well known for its high performance and capacity of the computer, and it is built in the motherboard itself, and of course its speed is slow compared to the previous levels, and the capacity of this cache may extend up to 8 MB. And now, what are the advantages of cache memory? Why we have to use cache memory? So we all know it is a faster memory, and also it is a costly memory, and also it is a small sized memory. It stores all the data and instructions which are required by the CPU that needs to improve the performance. So if some instructions are going to be executed more often, then the performance can be highly influenced if they are executed at a faster rate. So such type of instructions can be kept in the cache memory. Of course, the access time of data is very less when compared to that of the main memory and also at the remaining higher levels. Now coming to the disadvantages, as it is costlier and expensive, it has a limited storage capacity, and so the cache will get filled at the faster rate. So if the cache is going to be filled, then what we have to do to bring in the new item, I have to identify which item is going to be replaced. So we have so many such algorithms available to select the replacement. Of course this cache memory will be discussed in detail. The memory mapping policies also will be discussed in the later sessions. This completes the introduction about the cache memory. Then comes register memory. Of course the register memory is nothing but the registers which are available very close to the CPU or within the CPU. So inside the CPU, the arithmetic and logic unit is going to be an important unit, and to feed this arithmetic and logic unit, we have registers that will feed the data in a temporary fashion. So it is going to be part of the computer, and we have the number of registers and the size of the registers are going to be decided by the processor architecture. It temporarily stores the data and instructions, and it is well known for its high speed. Its speed is going to be very high compared to the other levels of memory. Of course, there will be only limited set of registers. So with this limited set of registers, we will be able to manipulate. And hope you people will be aware of the C programming language. So if in case of C programming languages, we have special data type called register data type, where we can make use of these registers to store our intermediate data that can improve the performance of the overall system. So if the number of registers is going to be limited, if all the registers are going to be utilized, then by default the data will be transferred to the memory itself. So now we will just tabulate the difference between the primary memory and the secondary memory. So the primary memory, otherwise called as the main memory, and the secondary memory is usually referred as an auxiliary memory. So usually the CPU will refer the data only directly with respect to the main memory, and it cannot be accessed directly at the secondary level. And of course all the main memory is going to be non-volatile, meaning that when the power is lost, the content is going to be lost, whereas all the secondary memory have permanent supports permanent storage capability. And of course the primary memory are going to be costlier, and of course they are faster when compared to the secondary memory, and capacity wise also it is going to be limited. Okay, then it required more power to retain the data, because it sometimes needs to refresh the content if it is going to make use of this dynamic RAM, whereas here no such power is required to retain the content. And some of the examples of the primary memory what we have discussed so far, like RAM, ROM, registers, EPROM, PROM, all variants of ROM, and the cache memory, all will come under the category of main memory. And all the memory which are going to be external to the computers, which are connected as an output device or input device, that is going to be referred to secondary memory, like CDs, DVDs, HDDs, man tape, flash disk, optical disk, pen drives, etc. So this is going to compare, we will give you a comparative view about the main memory and the secondary memory. And now we will just discuss how actually the memory is going to be organized in the form of the chips. So maybe we will just see the diagram here. So this is going to be the sample diagram for a processor architecture, how this RAM and ROM chip is going to be made available. So if we just see the RAM chip here, we will just note down that there are chip select signal CS1 and CS2 bar. So actually there are two chip select signals available, and if the chip select signal, this line is high, it is active high, this will be activated, and if it is low, this is active low, so this signal will be activated. And the size of this memory is given as 128 by 8, 128 by 8. So that means totally 128 locations, each location can store 8 bit of data. And because it is storing 8 bit of data, the data bus will be able to support 8 bits at a time. So the width of the data bus is also 8 bit, and totally we have 128 locations available in the RAM, and these locations will be addressed from starting address 0 to 127. And with respect to memory, usually the CPU will be able to perform two operations. One is read operation, another one is write operation. So with the help of this read, it will start reading the information available inside the memory. For that purpose, it has to give the address. So the address will be available in this AD7. So this is not a single line. Actually, it is going to be, it is referred as AD0 to AD7, totally 8-bit address line. Why we need 8-bit address line? If there are 8 bits, we can address 2 power 8 locations. That means totally 256 locations can be addressed. And we have only 128. So to address 128, we need 7 bits. So 2 power 7 is equal to 128. So the address will start from the range 0 to 127. So 0 to 127, totally 128 locations. So in order to address any one of these locations, we need 7 bits. So for that purpose, we have a 7-bit address, and it is going to be referred as AD0 to AD6. Actually, AD6, it will refer 7-bit of information. Okay, totally 7 bits. Okay. So the data bus will carry the data, and the address bus will carry the address. So whenever the user or the CPU wants to read something from the memory, he will first place the address in the address bus. He will activate the chip select signal, and then he will activate the read control line. So activated the read control line and the address, the information available in that address will be made available in the data bus for output. And whenever we want to write something into the memory, then the content will be placed in the data bus from the buffer register, and then in which address it has to be written. So the 7-bit address information will be kept in the address bus, and then the write signal will be activated. So the data will be transferred. So this completes a block diagram of a RAM chip. Now coming to this ROM chip, we all know read only. It is only read. So there is no write operation. So if you just compare these two memory blocks, the difference is this read and write control signal will be missing here. Why it is missing? We are not going to do write operation. Always it is going to perform, we are going to perform only read operation, and so there is no need to separately give a control line. And the chip lines will be activated. Of course, here if you just see the size of the memory is 512. So 512 means you can address 512 locations only if you have a 9-bit information. So to 8-bit you can address 256 locations. So with 9-bit you can address 512 locations. We have to address anyone among 5 512. So the address bit will be 2 power 9. So it will be able to generate 512 address symbols starting from the number 0 to 511. So given this address in this address line and then activated the chip select line, whatever is there, it is available in the memory, it will be made available in the 8-bit database. Of course, the length of each location is going to be 8-bit here also 8-bit. That refers to one word. Okay, this completes the discussion of this ROM chip. Now coming to the function table. So this function table will specify what type of function will be performed with respect to memory. So we have two chip select lines, CS1 and CS2 bar, and then with respect to this memory RAM, we have this read line and write line, and what is the memory function it is going to implement, and what is going to be the state of state of the data bus. So if this CS1 is 0 and CS2 bar is 0, we all know that if it is 0, this will be activated, second line will be activated. And even if the second line is activated, if we are not going to do either read function or write function, that is we are just representing it as a don't care operation, then the memory function is inhibited. So for both the cases, the memory function is inhibited. So for this combination, nothing will happen. You are not going to do any read operation or write operation. That means the bus will be kept in the high impedance state. So you are not going to make use of the bus content. Then we will start one by one. Of course, if you are going to deal with the chip select 2 signal, then this will be high and this will be 0. So for all these three combinations, I think second chip will be activated, and when it is activated, you will be performing either the write operation or the read operation. So read operation will be done if this read signal is activated, and write operation will be done if write signal is activated. And if both are not activated, that is 0 0 means it is going to be the inhibit, and there also the high impedance state will be continuing. So whether we are going to input the information into the chip or we are going to get output from the chip, that is going to be decided by this signal combinations. And again, if it is going to be 1 1 1 1, the chip select signal 0 0 and 1 1, both is going to keep it in the high impedance state. That means inhibit state. So you are not going to do any of this operation. So always the function table will explain you what type of operations will be carried out on the RAM chip. It can either undergo read operation or write operation or simply inhibit operation. So this inhibit operation will happen either if this chip select signal is going to be 0 or 1. So the main important point is here this read and write. If the read and write are not going to be activated, it is not going to perform any operation. So it will be kept in the high impedance state. So this is going to be an example of the memory address map which is maintained in the computer. There we have 4 RAM chips and 1 ROM. So 128, one chip is going to offer 128 byte size. Like this, we are going to have 4 into this many size. So this is going to be the total size of memory address that can be addressed, and there is only one ROM chip of size 512 bytes. So here the address bus will be able to carry the 7-bit address informations or sometimes 9-bit address. So it is going to be a common map given. So if you just go through this diagram, I think it will be clear. So the address range also has been given, just for an example of how the memory is going to be used. This completes the discussion of memory system. Thank you.